A derailment is said to take place when a vehicle such as a train runs off its rails. This does not necessarily mean that it leaves its track. Although many derailments are minor, all result in temporary disruption of the proper operation of the railway system, and they are potentially seriously hazardous to human health and safety. Usually, the derailment of a train can be caused by a collision with another object, the mechanical failure of tracks, such as broken rails, or the mechanical failure of the wheels. History: in the 19th century derailments were commonplace, but progressively improved safety measures have resulted in a stable lower level of such incidents. In the U.S., derailments have dropped dramatically since 1980 from over 3,000 annually to 1,000 or so in 1986, to about 500 in 2010. Causes: derailments result from one or more of a number of distinct causes. These may be classified as the primary mechanical failure of a track component failure, the primary mechanical failure of a component of the running gear of a vehicle, a fault in the geometry of the track components or the running gear that results in a quasi-static failure in running, a dynamic effect of the track-vehicle interaction, improper operation of points, or improper observance of signals protecting them, as a secondary event following collision with other trains, road vehicles, or other obstructions, train handling. Broken rails. A traditional track structure consists of two rails, fixed a designated distance apart, and supported on transverse sleepers. Some advanced track structures support the rails on a concrete or asphalt slab. The running surface of the rails is required to be practically continuous and of the proper geometrical layout. In the event of a broken or cracked rail, the rail running surface may be disrupted if a piece has fallen out, or become lodged in an incorrect location, or if a large gap between the remaining rail sections arises. 170 broken rails were reported on Network Rail in the UK in 2008, down from a peak of 988 in 1998/1999. In jointed track, rails are usually connected with bolted fish plates. The web of the rail experiences large shear forces and these are enhanced around the bolt hole. Where track maintenance is poor, metallurgical fatigue can result in the propagation of star cracking from the bolt hole. In extreme situations this can lead to a triangular piece of rail at the joint becoming detached. Metallurgical changes take place due to the phenomenon of gauge corner cracking, and also due to the effects of hydrogen inclusion during the manufacturing process, leading to crack propagation under fatigue loading. Local embrittlement under the parent metal may take place due to wheel spin. Rail welds may fail due to poor workmanship. This may be triggered by extremely cold weather or improper stressing of continuously welded rails, such that high tensile forces are generated in the rails. The fish plates in jointed track may fail, allowing the rails to pull apart in extremely cold weather. This is usually associated with uncorrected rail creep. Derailment may take place due to excessive gauge widening, in which the sleepers or other fastenings fail to maintain the proper gauge. In lightly engineered track where rails are spiked to timber sleepers, spike hold failure may result in rotation outwards of a rail, usually under the aggravating action of crabbing of bogies on curves. The mechanism of gauge widening is usually gradual and relatively slow, but if it is undetected, the final failure often takes place under the effect of some additional factor, such as excess speed, poorly maintained running gear on a vehicle, misalignment of rails, and extreme traction effects. The crabbing effect referred to above is more marked in dry conditions, when the coefficient of friction at the wheel-to-rail interface is high. Defective wheels. The running gear wheel sets, bogies, and suspension may fail. The most common historical failure mode is collapse of plain bearings due to deficient lubrication, and failure of leaf springs. Wheel tires are also prone to failure due to metallurgical crack propagation. Modern technologies have reduced the incidence of these failures considerably, both by design and intervention. Unusual track interaction. If a vertical, lateral, or cross-level irregularity is cyclic and takes place at a wavelength corresponding to the natural frequency of certain vehicles traversing the route section, there is a risk of resonant harmonic oscillation in the vehicles, leading to extreme improper movement and possibly derailment. This is most hazardous when a cyclic roll is set up by cross-level variations, but vertical cyclical errors also can result in vehicles lifting off the track. This is especially the case when the vehicles are in the tear condition, and if the suspension is not designed to have appropriate characteristics. The last condition applies if the suspension springing has a stiffness optimized for the loaded condition, or for a compromise loading condition, so that it is too stiff in the tear situation. The vehicle wheel sets become momentarily unloaded vertically so that the guidance required from the flanges or wheel tread contact is inadequate. A special case is heat-related buckling. In hot weather the rail steel expands. This is managed by stressing continuously welded rails and by providing proper expansion gaps at joints and ensuring that fish plates are properly lubricated. In addition, lateral restraint is provided by an adequate ballast shoulder. If any of these measures are inadequate, the track may buckle. A large lateral distortion takes place, which trains are unable to negotiate. Improper operation of control systems junctions and other changes of routing on railways are generally made by means of points. In the early days of railways these were moved independently by local staff. Accidents usually collisions took place when staff forgot which route the points were set for, or overlooked the approach of a train on a conflicting route. If the points were not correctly set for either route set in mid-stroke it is possible for a train passing to derail. The first concentration of levers for signals and points brought together for operation was at Bricklayers Arms Junction in southeast London in the period 1843 to 1844. The signal control location was enhanced by the provision of interlocking in 1856. To prevent the unintended movement of freight vehicles from sidings to running lines, and other analogous improper movements, trap points and derails are provided at the exit from the sidings. In some cases these are provided at the convergence of running lines. It occasionally happens that a driver incorrectly believes he has authority to proceed over the trap points, or that the signaller improperly gives such permission. This results in derailment. The resulting derailment does not always fully protect the other line. A trap point derailment at speed may well result in considerable damage and obstruction, and even a single vehicle may obstruct the clear line. Derailment following collision if a train collides with a massive object, it is clear that derailment of the proper running of vehicle wheels on the track may take place. Although very large obstructions are imagined, it has been known for a cow straying onto the line to derail a passenger train at speed such as occurred in the Pomont rail accident. The most common obstructions encountered are road vehicles at level crossings. Malicious persons sometimes place materials on the rails, and in some cases relatively small objects cause a derailment by guiding one wheel over the rail. Derailment has also been brought about in situations of war or other conflict, such as during hostility by Native Americans, and more especially during periods when military personnel and materiel was being moved by rail. Harsh train handling the handling of a train can also cause derailments. The vehicles of a train are connected by couplings. In the early days of railways these were short lengths of chain that connected adjacent vehicles with considerable slack. Even with later improvements there may be a considerable slack between the traction situation and power unit braking. This results in coupling surge. More sophisticated technologies in use nowadays generally employ couplings that have no loose slack, although there is elastic movement at the couplings. Continuous braking is provided, so that every vehicle on the train has brakes controlled by the driver. Generally this uses compressed air as a control medium, and there is a measurable time lag as the signal propagates along the train. If a train driver applies the train brakes suddenly and severely, the front part of the train is subject to braking forces first. The rear part of the train may overrun the front part, and in cases where coupling condition is imperfect, the resultant sudden closing up may result in a vehicle in tear condition being lifted momentarily, and leaving the track. This effect was relatively common in the 19th century. On curved sections, the longitudinal forces between vehicles have a component inward or outward respectively on the curve. In extreme situations these lateral forces may be enough to encourage derailment. A special case of train handling problems is overspeed on sharp curves. This generally arises when a driver fails to slow the train for a sharp curved section in a route that otherwise is higher speed conditions. In the extreme, this results in the train entering a curve at a speed at which it cannot negotiate the curve, and gross derailment takes place. The specific mechanism of this may involve bodily tipping but is likely to involve disruption of the track structure and derailment as the primary failure event, followed by overturning. An example of speeding on a curve would be the May 2015 Philadelphia train derailment involving an Amtrak train traveling at 106 miles per hour, twice the maximum allowable speed of 50 miles per hour. Flange climbing. The guidance system of practical railway vehicles relies on the steering effect of the conicity of the wheel treads on moderate curves. On sharper curves, flange contact takes place, and the guiding effect of the flange relies on a vertical force. A flange climbing derailment can result if the relationship between these forces, LV, is excessive. The lateral force L results not only from centrifugal effects, but a large component is from the crabbing of a wheel set, which is a non-zero angle of attack during running with flange contact. The LV excess can result from wheel unloading, or from improper rail or wheel tread profiles. A physics of this is more fully described below, in the section wheel-rail interaction. Wheel unloading can be caused by twist in the track. This can arise if the cant of the track varies considerably over the wheelbase of a vehicle, and the vehicle suspension is very stiff in torsion. In the quasi-static situation, it may arise in extreme cases of poor load distribution, or on extreme canted low speed. If a rail has been subject to extreme sidewear, or a wheel flange has been worn to an improper angle, it is possible for the LV ratio to exceed the value that the flange angle can resist. If weld repair of side-worn switches is undertaken, it is possible for poor workmanship to produce a ramp in the profile in the facing direction, that deflects an approaching wheel flange onto the rail head. In extreme situations, the infrastructure may be grossly distorted or even absent. This may arise from earthworks movement, earthquake and other major terrestrial disruption, deficient protection during work processes, etc. Wheel-rail interaction. Nearly all practical railway systems use wheels fixed to a common axle. The wheels on both sides rotate in unison. Tram cars requiring low floor levels are the exception, but much benefit in vehicle guidance is lost by having unlinked wheels. The benefit of linked wheels derives from the conicity of the wheel treads. The wheel treads are not cylindrical, but conical. On idealized straight track, a wheel set would run centrally, midway between the rails. The example shown here uses a right curving section of track. The focus is on the left side wheel, which is more involved with the forces critical to guiding the rail car through the curve. Diagram 1 below shows the wheel and rail with the wheel set running straight and central on the track. The wheel set is running away from the observer. Diagram 2 showed the wheel set displaced to the left, due to curvature of the track or a geometrical irregularity. The left wheel is now running on a slightly larger diameter. The right wheel opposite has moved to the left as well, towards the center of the track, and is running on a slightly smaller diameter. As the two wheels rotate at the same rate, the forward speed of the left wheel is a little faster than the forward speed of the right wheel. This causes the wheel set to curve to the right, correcting the displacement. This takes place without flange contact. The wheel sets steer themselves on moderate curves without any flange contact. The sharper the curve, the greater the lateral displacement necessary to achieve the curving. On a very sharp curve, the width of the wheel tread is not enough to achieve the necessary steering effect, and the wheel flange contacts the face of the high rail. Diagram 3 shows the running of wheel sets in a bogie or a four-wheeled vehicle. The wheel set is not running parallel to the track. It is constrained by the bogie frame and suspension, and it is yawing to the outside of the curve. That is, its natural rolling direction would lead along a less sharply curved path than the actual curve of the track. The angle between the natural path and the actual path is called the angle of attack. As the wheel set rolls forward, it is forced to slide across the railhead by the flange contact. The whole wheel set is forced to do this, so the wheel on the low rail is also forced to slide across its rail. This sliding requires a considerable force to make it happen, and the friction force resisting the sliding is designated L, the lateral force. The wheel set applies a force L outwards to the rails, and the rails apply a force L inwards to the wheels. Note that this is quite independent of centrifugal force. However, at higher speeds the centrifugal force is added to the friction force to make L. The load on the outer wheel is designated V, so that in diagram 4 the two forces L and V are shown. The steel-to-steel contact has a coefficient of friction that may be as high as 0.5 in dry conditions, so that the lateral force may be up to 0.5 of the vertical wheel load. During this flange contact, the wheel on the high rail is experiencing the lateral force L, towards the outside of the curve. As the wheel rotates, the flange tends to climb up the flange angle. It is held down by the vertical load on the wheel V, so that if LV exceeds the trigonometrical tangent of the flange contact angle, climbing will take place. The wheel flange will climb to the railhead where there is no lateral resistance in rolling movement, and a flange climbing derailment usually takes place. In diagram 5 the flange contact angle is quite steep, and flange climbing is unlikely. However, if the railhead is side-worn or the flange is worn, as shown in diagram 6 the contact angle is much flatter and flange climbing is more likely. Once the wheel flange has completely climbed onto the railhead, there is no lateral restraint, and the wheel set is likely to follow the yaw angle, resulting in the wheel dropping outside the rail. An LV ratio greater than 0.6 is considered to be hazardous. It is emphasized that this is a much simplified description of the physics. Complicating factors are creep, actual wheel and rail profiles, dynamic effects, stiffness of longitudinal restraint at axle boxes, and the lateral component of longitudinal forces. Re-railing. Following a derailment, it is naturally necessary to replace the vehicle on the track. If there is no significant track damage, that may be all that is needed. However, when trains in normal running derail at speed, a considerable length of track may be damaged or destroyed. Far worse secondary damage may be caused if a bridge is encountered. With simple wagon derailments where the final position is close to the proper track location, it is usually possible to pull the derailed wheel sets back onto the track using re-railing ramps. These are metal blocks designed to fit over the rails and to provide a rising path back to the track. A locomotive is usually used to pull the wagon. If the derailed vehicle is further from the track, or its configuration make the use of ramps impossible, jacks may be used. In its crudest form, the process involves lifting the vehicle frame and then allowing it to fall off the jack towards the track. This may need to be repeated. A more sophisticated process involves a controlled process using slewing jacks in addition. Photographs of early locomotives often indicate one or more jacks carried on the frame of the locomotive for the purpose, presumed to be a frequent occurrence. When more complex re-railing work is needed, various combinations of cable and pulley systems may be used, or the use of one or more rail-borne cranes to lift a locomotive bodily. In special cases road cranes are used, as these have greater lifting and reach capacity, if road access to the site is feasible. In extreme circumstances, a derailed vehicle in an awkward location may be scrapped and cut up on site, or simply abandoned as non-salvageable. Examples: note, there is a large list of railway accidents in general at lists of rail accidents. Primary mechanical failure of a track component equals, in the Hatfield rail crash in England in 2000, rolling contact fatigue had resulted in multiple gauge corner cracking in the surface. 300 such cracks were subsequently found at the site. The rail cracked under a high-speed passenger train, which derailed. 4 persons died. In the earlier Hither Green rail crash, a triangular segment of rail at a joint became displaced, and lodged in the joint. It derailed a passenger train and 49 persons died. Poor maintenance on an intensively operated section of route was the cause. Primary mechanical failure of a component of the running gear of a vehicle equals, in the Escher train disaster in Germany, a high-speed passenger train derailed in 1998, killing 101 people. The primary cause was the fracture from metal fatigue of a wheel tire. The train failed to negotiate two sets of points and struck the pier of an overbridge. It was the most serious railway accident in Germany, and also the most serious on any high-speed line. Ultrasonic testing had failed to reveal the incipient fracture. Dynamic effects of vehicle-track interaction. In 1967 in the UK there were 4 derailments due to buckling of continuously welded track. At Lichfield on June 10, an empty car-flat train. On June 13 an express passenger train was derailed at Somerton. On July 15 a Freightliner train was derailed at Leamington. And on July 23 an express passenger train was derailed at Sandy. The official report was not entirely conclusive as to the causes, but it observed that the annual total of buckling distortions was 48 in 1969, having been in single figures in every previous year, and that heat-related distortions per 1,000 miles per annum were 10.42 for CWR and 2.98 for jointed track in 1969, having been a maximum of 1.78 and 1.21 in the previous 10 years. 90% of the distortions could be attributed to one of the following: failure to comply with the instructions for laying or maintaining CWR track, recent interference with the consolidation of the ballast, the effect of discontinuities in the CWR track such as points etc., extraneous factors such as formation subsidence. Improper operation of control systems. In the Conington South Rail crash on March 5, 1967 in England, a signaller moved the points immediately in front of an approaching train. Mechanical signalling was in force at the location, and it was believed that he improperly replaced the signal protecting the points to danger just as the locomotive passed it. This released the locking on the points and he moved them to lead to a loop line with a low speed restriction. The train, traveling at 75 miles per hour, was unable to negotiate the points in that position and 5 persons died. The signaller had seen Army service and was probably suffering from what is now called post-traumatic stress syndrome. Secondary events following collision. A passenger train was derailed in the Pomont rail accident in the UK in 1984 upon hitting a coward speed. The train formation had the locomotive at the rear with a light driving trailer vehicle leading. The cow had strayed onto the line from adjacent agricultural land, due to deficient fencing. 13 persons died in the resulting derailment. However, this was thought to be the first occurrence from this cause since 1948. Train handling effects. The Salisbury rail crash took place on July 1, 1906. A first-class only special boat train from Stonehousebool, Plymouth, England, ran through Salisbury station at about 60 miles per hour. There was a sharp curve of 10 chains radius and a speed restriction to 30 miles per hour. The locomotive overturned bodily and struck the vehicles of a milk train on the adjacent line. 28 people were killed. The driver was sober and normally reliable, but had not driven a non-stopping train through Salisbury before. There have been several other derailments in the UK due to trains entering speed-restricted sections of the track at excessive speed. The causes have generally been inattention by the driver due to alcohol, fatigue or other causes. Prominent cases were the Nuneaton rail crash in 1975, the Morpeth accident in 1984 restricted sharp curve at full speed. Alcohol a factor. No fatalities due to the improved crashworthiness of the vehicles. Geometry faults that result in quasi-static failure. See also: lists of rail accidents, train wreck, tram accident, guard rails. Notes. References. Further reading: Iwanicki, Simon, ed. Handbook of Railway Vehicle Dynamics. Boca Raton, Florida, Taylor and Francis. ISBN 978-0-8493-3321-7.